The oceans of our planet are crossed by true giants, ships the size of skyscrapers, capable of carrying tens of thousands of containers, thousands of cars, and even carving a path through Arctic ice. Today, you are in for 2 hours of incredible stories about the biggest ships and the most powerful transport systems in the world. You will see how the largest container ships on the planet are built, look inside a legendary icebreaker, learn how vessels transport 10,000 cars in a single voyage, and also how the most powerful army on Earth is moved. Before we begin, I would like to ask you to like this video and subscribe to the channel. Make yourselves comfortable. We are beginning. Before you is MSC Irina, the largest container ship ever built by humans. When you see this colossus preparing to take on cargo, the first thing that literally hits your perception is its scale. It is not just big, it is overwhelmingly huge. From bow to stern, the vessel stretches for 1,312 feet. That is almost a quarter of a mile in length. If you were standing at its base in a dry dock and lifted your head up, you would be facing a solid steel wall about as tall as a 15-story building. But size is only part of the story. The real amazement begins when you realize ships like this do things that seem impossible. And they do it with a crew whose head count is smaller than that of a professional American football team. The first thing that seems unbelievable is the volume of cargo. Container ships measure capacity in TEU, meaning 20-foot equivalent units. 1 TEU is a standard shipping container 20 feet long. MSC Irina can carry more than 24,000 TEU, 24,000 metal boxes, each filled with goods, stacked into rows that run the entire length of the ship and rise 24 containers above the deck. And then a fair question appears. How does something this top-heavy not capsize? The answer is engineering brought to perfection. If you look below the waterline, on both sides of the hull, you can see huge ballast tanks. These are special compartments that can be filled with seawater when needed or drained. When the ship is fully loaded with containers towering above the deck, the ballast tanks are filled with water. This lowers the center of gravity and makes the ship stable. When the ship travels empty, the water is pumped out so it does not sit too deep. In addition, the ship has a wide flat bottom and a massive keel that works like the weighted base of a boxing punching bag. Every time the vessel lists, that weight literally pulls it back toward the upright position. The engineers who designed ships like this calculated precisely how many containers can be stacked on top of each other before stability becomes a problem. The result is a ship that looks like it is about to tip over, but in reality stays stable even in waves 40 feet high. But before heading out to sea, the ship has to be loaded. And this process is a separate engineering miracle. When a container ship enters a port, time immediately starts working against it. Every hour at the berth is an hour when it is not carrying cargo across the ocean. And that means loading is refined to the precision of seconds. The main heroes of this process are ship-to-shore gantry cranes. These are giant steel structures rising more than 200 feet above the quay. They move on rails along the pier and are positioned precisely over the ship's cargo holds. A major port can deploy a whole dozen of these cranes, working at the same time on a single ship. But before a crane lifts a container, it has to be delivered to the ship's side. This is where straddle carriers come in. Tall, narrow machines that look like moving construction scaffolding on wheels. They drive directly over a container, lower a top-lift spreader, pick up the cargo between their legs, and carry it across the yard to the spot where the gantry crane is already waiting. In a busy terminal, there can be dozens of these machines. They work non-stop, like a conveyor belt, feeding containers to the cranes. Without them, the cranes would simply sit idle, waiting for cargo. And this is where work begins, that is far more complex than it looks from the outside. Loading containers is not an arcade claw game. Each crane lowers a device called a spreader. This is a metal frame that can expand or contract for containers that are 20 or 40 feet long. If you look closely at the corners of any container, you will see reinforced steel pieces with oval holes, corner castings. That is where the twist locks go. When the spreader is lowered onto a container, 4 twist locks enter the corner castings and rotate 90 degrees, locking the load. The whole operation takes about 2 seconds. After that, the container is lifted, carried over the ship, lowered into place, and the locks are released. An experienced crane operator can move 30 to 40 containers per hour. With several cranes working, a ship can be fully loaded in less than 24 hours. But speed is only half the task. The second, no less difficult part is figuring out where exactly each container must go. Even before the ship approaches the port, a detailed stowage plan has already been prepared for it. Every container has a strictly defined position. Visually, it looks like a giant game of Tetris, but here there are no accidents and no improvisation. Containers that must be unloaded at the first port of call are placed closer to the top. The heaviest ones are placed lower to keep the center of gravity as low as possible. Refrigerated containers, those that require cooling, are placed near power connections. Dangerous goods must be kept at a strictly defined distance from one another, and at the same time, the planner has to ensure the ship remains balanced not only side to side, but also from bow to stern. An error in the calculations can lead to a list, or worse, to dangerous stresses on the hull. So when you see cranes simply moving boxes around, in reality, behind every lift, there is invisible coordination. Planners, crane operators, port systems, and the ship's officers work as a single organism, turning chaos into order. After loading, a new problem appears: how to keep 24,000 metal boxes from being thrown overboard in the open ocean. A container ship at sea does not just move forward. It rolls from side to side, buries its bow into waves, slams into crests with such force that vibration runs through the entire hull. Any poorly secured container turns into a dangerous projectile. Containers do fall overboard. On average, about 1,500 containers a year are lost in the ocean. But if you consider that more than 250 million containers are transported by sea every year, that number is strikingly small. The cargo securing system works as follows. Containers located below deck are placed inside holds in special vertical guides, cell guides. They fit into the corner castings of the containers and hold them like pieces of a mosaic. Such containers practically do not need additional securing. The guides prevent sideways movement and hold the cargo even in heavy rolling. The situation on deck is much more complicated. There, the containers stand under the open sky, and they are held only by a combination of friction and fastening hardware. Between containers, twist locks are used, similar to those used by cranes, but intended for permanent securing. They connect the upper and lower container through the corner castings. The bottom container in each stack is attached to deck locks that connect it directly to the ship's structure. But for the upper levels, that is not enough. This is where lashing rods come in, long steel bars that run diagonally from the upper containers down to securing points on the deck. On these rods, there are turnbuckles that allow the crew to tighten them into a state of constant tension. As a result, the entire stack is as if pulled inward, resisting the forces that try to push the containers outward during rolling. Looking at such a tower, a logical question arises. How do the lower containers withstand the colossal weight? A 10-high stack can press on the bottom container with a force of more than 250 tons. But containers are designed for exactly such loads. Most of the strength is concentrated in the corner castings and vertical posts. The weight is transmitted strictly downward through the frame. The walls carry almost no load. Every standard container is certified for a load of no less than 192 tons, and most models significantly exceed that figure. Despite automation, this critically important stage remains manual. The workers who install and check all the securing equipment are called stevedores. They do this work by hand, in any weather, day and night. For one ship, thousands of individual securing points may be required, each one of which must be installed and checked before departure. This is one of the hardest and least visible professions in global logistics. When the containers are loaded and securely fixed, control fully transfers to the bridge. This is where all decisions about course, speed, and navigation are made, and it is located, at first glance, in the strangest place. On most container ships, the bridge is located at the stern, in the very back of the vessel. Ahead of it are hundreds of feet of containers stacked in dozens of rows and rising to a height of up to 24 containers. From the bridge windows, the crew is essentially looking at a wall of metal that completely blocks a direct view forward. But on the largest container ships in the world, this arrangement is radically changed. On the biggest ships, the bridge is shifted far forward and sits only 6 rows of containers from the bow. This is not a design flourish and not an engineer's whim. This placement frees the central part of the hull for uninterrupted container stacks, increases TEU capacity, and at the same time allows formal compliance with visibility requirements over the bow, even with the deck fully loaded. But if you look at the ship from the side, it becomes obvious. Even with this shift, the crew still cannot see what is directly in front of the bow. So how do they steer a ship without seeing where they are going? The answer is on the bridge consoles. In front of the crew is a whole set of screens and systems. Radar shows all vessels within a radius of 20 nautical miles. GPS provides positioning accuracy to within a few feet. An electronic chart system shows a digital map of the ocean with the ship's current position, depths, coastline, and navigational hazards. This system is called ECDIS, Electronic Chart Display and Information System. But the key solution to the blind spot problem is a forward video surveillance system. Modern container ships are equipped with cameras installed on the bow and on the forward mast. Live video is transmitted to the bridge monitors. Some ships use thermal cameras for night operations. Others are fitted with lidars capable of detecting objects that may not appear in camera view. There is also a simpler approach. The bridge itself is built on a high superstructure that raises it above the deck and gives officers a better viewing angle over the container stacks. But even then, forward visibility remains limited, so the crew trusts instruments more than eyes. The bridge operates around the clock. The crew stands watch in shifts. Usually a watch includes an officer responsible for navigation and collision avoidance, as well as a helmsman who monitors the autopilot and, if necessary, takes manual control. The captain does not stand watch continuously, but is called to the bridge in any non-standard situation. And yes, in most cases, these ships steer themselves. Modern autopilot systems can hold a course, compensate for wind and current, and follow pre-programmed routes across the entire ocean. But a human is always watching. The ocean is unpredictable. Traffic conditions change. Weather can deteriorate sharply. The autopilot takes over the routine. All non-standard decisions remain with the crew. Communication is provided by several redundant systems. VHF radio connects the ship with other vessels and shore services. Satellite systems provide voice communication and data transmission anywhere on the planet. When approaching a port, the bridge coordinates actions with pilots, tug captains, and vessel traffic services. The most unexpected thing is the size of the crew. On a ship of this size, there are usually only a few dozen people, and that is all. For a structure that in size surpasses the Empire State Building, these people remain completely alone in the middle of the ocean. The ship becomes their home. The crew's living quarters are usually located in the superstructure, in that very tower where the bridge is. Inside, there is nothing extra, but everything necessary. Officers have separate cabins. Junior crew have shared rooms. There is a mess hall where the crew gathers for meals, a small gym, a lounge with a television, sometimes a tiny library or a game area. This is not luxury and not a cruise. Ocean views impress you only for the first few days. After several weeks, the monotony begins to press down. These people are not passengers. They are working seafarers. Their job is to keep the ship moving, and that work does not stop day or night. An MSC Irina crossing of the Pacific can take about 2 weeks without a single stop. During that time, the crew's life follows a strict rhythm. Watches run around the clock. A typical pattern is 4 hours on duty, 8 hours of rest, and then again and again, with no weekends and no holidays. During watch, officers control the bridge. Engineers monitor the engine room. And that is far more complex than simply glancing at instruments and mopping floors. The power plant of such a vessel is one of the largest engines ever created by humans. We are talking about a 2-stroke diesel engine that rises to the height of 4 stories, stretches more than 80 feet in length, and produces more than 80,000 horsepower. At cruising speed, it burns from 150 to 300 tons of fuel per day. The crankshaft alone weighs more than 300 tons. If you go down into the engine room, you find yourself in a labyrinth of walkways, pipelines, and control stations spread across multiple decks. The noise here is deafening. The temperature is exhausting. Engineers make rounds in protective ear defenders and sweat-soaked coveralls. They check readings, listen for vibrations, and look for any deviation from normal. Computer systems automatically detect most faults. But no automation can replace a person who personally walks every section. A small leak noticed in time is routine maintenance. That same leak, ignored 3,000 miles from the nearest port, can turn into a catastrophe. While engineers keep the power plant running, the deck crew handles everything else. And there is always plenty of work. Steel ships rust. That is inevitable. Salt, moisture, and time destroy any exposed surface. So a significant part of every voyage goes to fighting corrosion. The crew chips off old paint, treats rust spots, and applies new protective coatings. Sometimes you can see sailors hanging over the side in special bosun's chairs, painting sections of the hull that can only be reached at sea. In the industry, they even joke, a ship's voyage is just the interval between painting jobs. Routine is broken only by weather. When a storm front crosses the ship's course, everything changes. Work on deck stops. Everything unsecured is tied down. The bridge continuously tracks the situation, adjusting course and speed to reduce stress. In heavy conditions, containers can shift, lashings can fail, and the hull itself can experience extreme loads. The crew's job is to prevent that. But most days pass without drama. Work, food, sleep, work again. The ocean stretches to the horizon, uniform, calm, endless. And one morning, land appears on the radar screens. And then the most difficult part of the voyage begins. There is one thing almost nobody thinks about. A fully loaded container ship weighs more than 200,000 tons. At cruising speed, it moves at about 25 miles per hour, and it has no brakes. To stop a ship of that size using only its own engines requires from 1 to 2 nautical miles. Reverse thrust only gradually bleeds off speed, but inertia here is ruthless. Physics does not care how expensive the cargo is on board. That is exactly why, when approaching a port, a container ship begins slowing down long before entering the harbor. Even after that, it still carries far too much energy to berth safely on its own. At this moment, tugboats take the stage. As soon as the ship enters the port, a group of 4 to 6 tugboats forms around it. Some go to the bow, others take positions along the sides or at the stern. These vessels are tiny compared to the container ship, but their power is astonishing. Each tug can produce from 5,000 to 8,000 horsepower. Their task is to pull, push, and literally break the container giant's inertia during the final stage of maneuvering. If you look at the numbers, you realize how serious this is. One tugboat, pressing against the side of a container ship, can create a lateral force of more than 80 tons. Multiply that by 6 tugboats working in sync, and you get enough force to move 200,000 tons of steel sideways, centimeter by centimeter, precisely toward the berth. During this stage, communication does not break for a single moment. A pilot, who boarded earlier from a small vessel, coordinates actions between the bridge and the tug captains. Commands sound clear and without ambiguity. Tug on the starboard side, push at 50%, bow tug, pull left, stern tug, hold position. One mistake, one misunderstood order, and the ship can strike the pier or drift toward another vessel. When the distance to the berth shrinks to a minimum, the deck crew gets involved. They prepare the mooring lines, massive ropes and cables that will hold the ship in place. The first lines are sent from the bow and stern. They are dropped down, where port workers put them over bollards. The ship's winches take up the slack, slowly pulling the hull toward the berth's protective fenders. Then, additional lines follow. Spring lines, to keep the ship from moving forward or backward. Breast lines, to press the hull against the pier. A fully moored container ship can be held by 12 to 16 lines, each of them under tension measured in thousands of pounds. When all lines are tight and the gangway is lowered, the tugboats let the ship go and move away. The ship is secured, and almost immediately, the gantry cranes take their positions. Twist locks engage, containers begin rising from the deck, and somewhere far beyond the horizon, another ship like it is already sailing, repeating this endless cycle of global logistics. See you soon. But if container ships conquer the oceans, there are ships that have to go where ordinary vessels simply cannot survive. To the place where the ocean turns into solid ice. Before you is Polar Star, the only heavy icebreaker of the United States capable of reaching Antarctica. Look at the channel trailing behind her stern. This is only the first stretch of the journey. Ahead lies an ice corridor more than 70 miles long, one the ship must cut through solid, multi-year ice. Nearby, a fuel tanker is waiting, loaded with millions of gallons of diesel. If Polar Star cannot break through and escort it to McMurdo Station, 1,000 people will be forced to ration heat in the coldest place on Earth. Right now, the tanker is standing at the edge of the Ross Sea ice shelf. The engines are idling. The crew watches as the icebreaker fights the ice. Every hour the channel remains closed brings the moment closer when the weather window will slam shut for good. If you look at the ship's bow at the moment of impact, a key detail becomes noticeable. It is not sharp like the bow of ordinary ships. Its shape is a gentle wedge, tilted at roughly 30 degrees to the horizon. And it is precisely this angle that decides the outcome of the entire operation. When the ship moves forward, the bow does not cut the ice horizontally. It climbs up onto the surface, like a heavy truck driving up a loading ramp. Forward motion turns into upward motion, and then gravity takes over. Polar Star's propellers deliver 75,000 horsepower to the shafts, about 400 tons of thrust. Pushing against the bow's 30-degree slope, nearly half of that force turns into vertical pressure. 200 tons press the hull down into the ice, which is already supporting 13,000 tons of steel. Ice does not bend. Multi-year mass is too dense. It shatters. The pressure at the moment of impact exceeds 300 pounds per square inch, 10 times the pressure in a car tire, concentrated onto a few square feet of frozen ocean. A web of cracks spreads across the surface. When the bow crashes back down with a roar, it must withstand the same loads. At -20 degrees Fahrenheit, ordinary steel stops behaving like the metal we are used to. Under normal conditions, the atoms in steel are constantly vibrating, allowing the material to flex under load. As the temperature drops, those vibrations weaken. Below that mark, standard steel becomes brittle. It does not bend, it breaks. Polar Star's solution is microalloying. Microfractions of nickel, chromium, and manganese are added to the steel, less than 5% of the total composition. These atoms embed themselves into the crystalline lattice of iron. Upon impact, the energy does not travel in a straight line of destruction. It disperses. A crack begins to wander, losing strength. Each alloying atom works like a microscopic shock absorber. That is why the 2-inch hull can withstand up to 10,000 impacts in a single expedition without failing. The corridor widens slowly, only by a few dozen feet per impact. Behind the stern, the broken ice turns into a churning mass through which the tanker will later be able to pass. But time is working against them. At -22°F, open water loses heat quickly. New ice forms within hours. If they delay, the 70-mile channel becomes an obstacle again. The tanker will follow behind, close enough to make it through, and far enough not to interfere with the icebreaker's work. Right now, below the waterline, 75,000 horsepower is working at the limit, in a space where everything is measured in thousandths of an inch. This is where the machinery is the first to show fatigue. The tanker will follow the icebreaker in a few hours, close enough to pass through the channel before it refreezes, and far enough not to get in the icebreaker's way. But underwater, its own invisible battle is already underway, between metal, ice, and mechanics. Below the main deck, the engineering spaces feel like they belong to another world. Outside, -22°F. Inside the engine room, the temperature climbs to 105, a difference of 127 degrees across mere inches of steel. The source of that heat is a diesel-electric plant. Massive engines the size of a school bus spin generators capable of powering a small city. But there is a key feature here that people rarely think about. These engines are not directly connected to the propellers. On a normal ship, power is transmitted through a reduction gearbox, a system of metal gears spinning at thousands of revolutions per minute. In open water, such a setup runs steadily. Ice breaks that logic. Imagine a propeller spinning freely in slush and suddenly striking multi-year ice, dense as concrete. The blade stops instantly. The engine does not. It is still trying to spin at 1,800 revolutions per minute. All that stored energy has to go somewhere. In a direct drive system, it surges back through the gears. In the best case, it shears off gear teeth. In the worst case, it snaps the shaft. And then the ship is left without propulsion in the middle of a frozen ocean. The icebreaker solves the problem radically by breaking the mechanical connection. The diesel engines spin generators. The generators produce electricity, the equivalent of the same 75,000 horsepower, which, through cables as thick as a human arm, feeds electric motors mounted directly on the propeller shafts. The main advantage is control speed. Electricity can be managed in milliseconds. If you look at the RPM indicator during icebreaking operations, the needle is constantly jumping. A moment ago, the propeller was turning at 150 revolutions, moving through slush. The next second, it meets dense ice and the speed drops to 60. The ice breaks and the revolutions rise again. Each such fluctuation is a euter to the drivetrain that would destroy a mechanical system. The electric system absorbs these impacts. But even that is sometimes not enough. There are times when the ice is too thick. The ship's bow rides up, but the mast does not break. The vessel hangs there, as if freezing into the ice, while the propellers uselessly churn the water. It is precisely at this moment that a system comes into play, one that has long become a legend. Inside the hull, along both sides, there are ballast tanks. Pumps can move about 100,000 gallons of seawater from one side to the other in less than 1 minute. When that mass of water shifts, the ship begins to roll, first by a few degrees, then more strongly. That is enough to break the ice suction between the hull and the ice. The grip weakens, and the propellers find free water again. From the bridge, it looks like controlled chaos, but the method works. It has worked for decades. And yet even a ship like this has limits. Right now, a warning lights up on the main board, a leak near the propeller shaft seal. This is not an emergency yet, but it is a signal that cannot be ignored. Engineers set up portable pumps and introduce checks every 30 minutes. In 12 hours, divers will be able to go down. Until then, everyone watches the instrument readings closely. This voyage is a test not only for machinery. Polar Star carries 155 crew members and up to 35 scientists, almost 190 people who need to eat, sleep, breathe, and stay warm for months. That is roughly 600 meals a day, cooked in a galley the size of a standard studio. That is tens of thousands of gallons of fresh water every week, because the nearest port is 1,000 miles away. This water is not delivered, it is produced on board. Water is produced using reverse osmosis systems. Seawater is forced through membranes under pressure of about 800 pounds per square inch. Water molecules pass through, salt stays behind. But you pay for that with energy. Every gallon is electricity that the diesel generators must produce, and that means fuel. Fuel that cannot be replenished until the next port. Everything here is connected. Water, food, heat, energy. And nearly 200 lives depend on that chain. The living spaces are tight. Bunks are stacked 3 high. 8 to 12 people live in one room. Personal space shrinks to a single bunk and a narrow locker. Privacy is not discussed here. There is none. Over time, you either learn to sleep through the hum of engines, the impacts of the hull against ice, and announcements over the loudspeaker, or you do not, and you stop sleeping normally. But the schedule does not adjust to fatigue. The ship operates around the clock. The crew splits into shifts, 4 hours on watch, 8 hours off. The cycle repeats again and again, ignoring the time of day. In the Antarctic summer, the sun does not set for months. The body loses its reference points. Breakfast can be at midnight, watch can be at dawn. Sleep comes when the schedule allows, not when the body asks. During ice-breaking operations, the bridge runs in a state of maximum concentration. Commands are short and precise. The conning officer controls the ship's movement, setting course and speed. The helmsman reacts instantly, holding the bow on the weaker sections of ice. Nearby stands an assistant, translating commands into the positions of the propulsion levers. At first glance, it seems excessive, until you realize the helmsman's hands are on the wheel and his eyes are on the ice. The most important person on the bridge does not wear a uniform. This is the ice pilot. He reads the ice surface like a map. A darker color often means thinner ice. Fresh cracks point to weak zones. Compressed ridges cast shadows that reveal their height. The pilot directs the ship to where the ice is ready to give way. A good ice pilot saves hours. A great one saves the hull. Training young officers here is harsh. A ship of this size responds with delay. A rudder command given now begins to take effect only tens of seconds later. What you do in this moment determines what happens next. Here, anticipating matters more than reacting. One mistake, and the ship can be turned sideways, pinching the hull in ice before anyone can correct the situation. Off watch, time goes into equipment maintenance, workouts, and sleep, which is always short. Entertainment is limited to a small gym, a lounge with movies and card games. Connection to home works only when a satellite is available. Letters arrive with delays of weeks. By the 3rd month, days begin to blend together. The crew operates on autopilot until the ice finally yields to open water. But not all days are the same. Sometimes the alarm sounds at 3 in the morning, and in seconds, everything changes. The most dangerous thing on the ship is not the ice outside. The most dangerous thing is fire inside. The hull does not burn, but everything inside burns readily. A fire in a confined compartment quickly fills the space with smoke, and the temperature can, within minutes, exceed 1,000 degrees Fahrenheit. In polar waters, the crew is always alone with any emergency. There is nowhere to expect help from. That is why every crew member undergoes basic damage control training even before leaving port. Fires, flooding, pipeline damage, electrical failures, all of this is drilled in advance. Drills are regular and deliberately harsh. The alarm can sound at any time. Compartments are filled with simulated smoke. The lights are turned off. Mistakes here are costly. In control lockers, everything necessary is placed in advance. Fire-resistant suits, breathing apparatus, plugs, wedges, and pipe patches. No unnecessary complexity. Only what works when visibility is 0 and hands are shaking with adrenaline. If fire breaks out in the engine room, the carbon dioxide extinguishing system engages. CO2 displaces oxygen and smothers the flames in seconds. But along with the fire, it displaces people. Those inside have about 1 minute to get out. After that, there are no chances left. If fire is the fastest enemy, water is the most relentless. A crack below the waterline does not seep. It blasts a jet under pressure. Real protection here is the ship's design. Watertight doors close with lever clamps that press the door panel against a frame with a rubber seal. A properly dogged door withstands pressure that would tear an ordinary one apart. But closing such a door means making a decision in seconds. If someone is left inside, there is no way out. The current leak near the propeller shaft seal is not critical yet, but it requires constant monitoring. Engineers set up portable pumps and introduce checks every 30 minutes. In 12 hours, divers will be able to go down. Until then, the crew watches the gauges closely. The ship stops in a relatively clear space between ice ridges. Movement ceases. The drive is shut down. The propeller shaft is locked with mechanical clamps, completely eliminating rotation. Because next, people will be in a zone where any movement of a mechanism can cost a life. Only after the shaft is fully locked do the divers begin preparation. Under-ice dives are among the most dangerous operations in the Coast Guard. They wear dry suits designed for icy water, full-face masks with communications, gloves that allow them to work with tools despite the cold. Each diver drags a safety line behind him, the only link to the surface. To lose it means to end up under the shelf where there will be no help. The ice stretches for tens of miles. The bottom is hundreds of meters below. Alongside the divers, a metal platform is lowered with tools, lighting, and a repair kit. Carrying this gear alone is impossible. Drop a tool and you lose it forever. The work zone is where a rotating shaft meets the stationary hull. Tolerances here are measured in thousandths of an inch. The slightest shift and water finds a path inside. The divers install a composite clamp with a deformable gasket. Bolts are tightened strictly by procedure, evenly distributing the load. Everything is done by feel, with short commands over comms. Above, the instruments show the inflow of water decreasing. This is not a final repair. The ship has about 200 working hours, but that is enough to finish the mission and reach open water, where a full repair is possible. Escorting the tanker is important, but it is not the ship's only mission. On board Polar Star, there are 5 scientific laboratories capable of supporting research groups for months. Oceanographers, climatologists, biologists, all of them work here because only an icebreaker can bring them to where maps end and real data begins. For science, ice is not a barrier, it is access. Through holes cut in the ice, cranes lower research equipment into black water. The main instrument is the CTD rosette system, a metal frame about 6 feet tall, shaped like a carousel. Around the circumference are sampling bottles. In the center is a sensor package. CTD stands for conductivity, temperature, and depth. This design allows bottles to close at strictly set levels, collecting water from specific layers of the ocean. In real time, graphs of temperature and salinity appear on screens. As the instrument descends, layers become visible, where warm water meets cold, where fresh meltwater lies over a dense, salty mass. These vertical profiles show how polar oceans circulate, how heat moves, how water masses form around the continent. One such cast gives more information about ocean dynamics than months of satellite observations. But the most valuable archive is ice cores. Drills extract cylinders of snow and sea ice, layer by layer. Inside them are bubbles of air sealed at the moment the layer formed. This is the atmosphere of the past, the ratio of oxygen, the concentration of carbon dioxide and methane, the tiniest particles of dust. Antarctic cores let you look back hundreds of thousands of years to an era long before modern humans appeared. One successful sample can extend the climate record farther than any instrument created by humans. Work on board is a constant fight with conditions. Impacts with ice cause vibrations that knock instruments out of calibration. Temperature swings stress electronics. Humidity spikes every time hatches are opened. Scientists compensate with shock-absorbing mounts, climate cabinets, and repeated measurements. Data gathered over days can vanish in seconds if a freezer loses power or a sample crosses a temperature limit. But in the moment when the channel is open, all of that fades into the background. Nearby stands the tanker with millions of gallons of diesel fuel, waiting for the signal. At McMurdo Station, they have been preparing for this for weeks. The station sits on volcanic rock, but its fuel pier is made of ice. It is a frozen pier pushed out into the Sound and reinforced with layers of flooded seawater that freeze. The ice pier can withstand hundreds of tons of cargo. They build it up each winter and cut it back in summer. There is simply no other way to receive ships at a station that has no harbor. When the tanker moors, fuel lines connect its tanks to the station's storage. Pumps begin transferring at about 500 gallons per minute. The process stretches for almost 2 days. While fuel is pumped into McMurdo's storage, the operation does not stop for a minute. Diesel moves at about 500 gallons per minute, and the entire process takes almost 2 days. All this time, the crews work at maximum concentration. In parallel with the fuel, unloading begins. Cranes lift containers from the tanker's deck, food for the winter over personnel, equipment for future research, construction materials, medicines, spare parts, everything without which the station will not survive the next year. During unloading, Polar Star does not leave. The icebreaker holds position nearby and constantly monitors the condition of the channel. Ice never stands still. Currents and wind move it. A passage opened yesterday can start squeezing shut today. The propellers run in a ready state. The crew is prepared at any moment to move forward again and break a new path if the tanker's exit route comes under threat. After 72 hours, the operation is finished. About 2 million gallons of diesel fuel are now in McMurdo Station's tanks. That is enough to provide heat, electricity, and the operation of equipment for another year. For the station, this is not just a number. It is light in the laboratories. It is warmth in the living modules. It is the movement of vehicles across the ice. Antarctica remains behind the stern. The channel cut with such effort gradually disappears. The ice will close again, as if it had never existed. But that time was enough. Enough for the station to survive another year. Enough for the mission to be completed. However, ice is not the only challenge for sea giants. Every day, ships move across the oceans carrying thousands of cars at the same time. In front of you is K Asian Beauty. This sea giant stretches almost 604 feet in length. That is comparable to 2 football fields placed one after another. Its beam is about 100 feet, and these proportions are not chosen by accident. They help balance the colossal length of the vessel and its height, which above the waterline reaches the level of a 12-story building. Simply put, this really is a titan. The ship was built in 1994 and is equipped with a MAN B and W engine, Model 6 L60MC, produced by MAN Energy Solutions. The maximum power of the plant reaches 10,500 kilowatts, which is equivalent to approximately 14,000 horsepower. For an ordinary ship, such figures would look excessive, but for a cargo monster of this kind, it is a жизненная necessity. Not much is known about K Asian Beauty in open sources, however. With a high degree of confidence, one can assume that, like most ships of this class and era, it is equipped with a standard set of critically important systems. We are talking, in particular, about ballast tanks, and possibly elements of dynamic positioning, technologies that help a ship maintain stability and an exact position in one of the most responsible moments of its service, during berthing. When K Asian Beauty, after a 2-week passage from South Korea, enters the harbor of San Diego, a process begins that illustrates as well as possible the saying, "One man in the field is not a warrior." This is not a boat, and not a pleasure yacht that you can pull up to the pier by hand or secure with an anchor. Here, everything is completely different, and that is exactly what distinguishes such vessels from everything most people have ever seen. A key role in berthing is played by smaller vessels. Yes, that is right. Tugboats. These small but incredibly powerful workhorses accurately push and pull the mnogotysichtonny ship, step by step, aligning it relative to the pier. Their task is to achieve a perfect match with the quay wall. The pier itself is equipped with special fenders, massive shock-absorbing elements that serve as a buffer between the ship's hull and the concrete. They do not just prevent damage to the plating, but also absorb the inertia of a ship that cannot be stopped instantly. The berthing process is a complex choreography where every movement is calibrated down to the centimeter. Harbor pilots, specialists who know the local waters in detail, take control and lead the ship along the final route. At the same time, tides, the direction and strength of the wind, and the condition of the currents are all taken into account. But it does not end there. After the ship takes its place, mooring teams come into play. Mooring lines are secured on bollards, short but incredibly strong metal posts, like those you can see, for example, on the piers of Chicago. It is precisely they that hold the ship in a fixed position, not allowing waves or oscillations to move it from its place. This is especially important when we are talking about a ship with a displacement of about 20,000 tons, carrying almost 7,000 units of cargo. In essence, in front of us is a giant floating garage. On board the vessel, there are up to 13 decks, some of which are stationary and some adjustable. And that is logical. Agree, a sports car and a massive pickup require completely different placement conditions. Movable decks can be raised or lowered, creating additional space for taller vehicles or non-standard cargo. When all these elements work simultaneously, it becomes clear how difficult it is to manage such a vessel. One poorly secured vehicle is enough, and the balance of the entire structure can be disrupted. And what will happen if the center of gravity shifts too much? The consequences can be catastrophic. And of course, there is yet another level of control, that very person with the checklist who checks everything down to the last bolt. In this case, border control services. At the very moment when Asian Beauty completes berthing, inspection groups begin work with one single goal: to check absolutely everything. First of all, the ship's documents and the cargo manifest are studied. They contain complete information about the cargo being carried, the number of vehicles, their types, descriptions, and any accompanying goods. Then, the physical inspection begins. Inspectors walk the decks, examine the rows of vehicles, look into technical compartments and cargo spaces. Any discrepancy, and the item is immediately marked for additional investigation. History knows many such cases. One of the most illustrative happened in 2015 when Kenyan authorities discovered firearms and drugs hidden inside the tires of 3 military vehicles transported by the Norwegian ship Hogue Transporter. That is why control here is not a formality, but of a process safety, and not only the cargo is checked. Border control is not limited only to the cargo. No less close attention is paid to the people on board the ship. In global practice, there are frequent cases when outsiders get onto cargo ships, posing as crew members. It also happens that people are held on the ship against their will. That is why immigration services are obliged to make sure that every person on board has valid documents and that working conditions comply with international norms. Compliance with the requirements of the International Labor Organization is checked, including the provisions of the Maritime Labor Convention. These rules regulate everything, from the length of the working day to the living conditions of the crew. But even that is not the end of the checks. A separate block of inspections is devoted to ecology. The last thing coastal waters need is a careless attitude toward the environment. Inspectors thoroughly check how the ship handles waste and technical liquids. Special attention is paid to the fuel tanks. Specialists inspect them for leaks, check tightness, and the serviceability of all systems. The slightest malfunction can lead to pollution of the water, and for the port, this is a scenario they try to avoid at any cost. In addition to fuel, the systems for treating sewage water, garbage, and other waste accumulated during the voyage are checked. All of this must comply with international standards, including the requirements of MARPOL Annex 4, which regulates the discharge of waste into the sea. For example, the ship is obliged to have certified sewage treatment units or special tanks for storing them until disposal in port. Another critically important aspect is the ship's ballast system. Ballast is the foundation of a ship's stability. As a rule, ballast tanks are located in the lower part of the hull and can be filled with seawater or, conversely, emptied to maintain balance. This system works not only while underway. Even during the loading and unloading of vehicles, the ship can take in or discharge ballast water, compensating for the weight of added or removed cargo. Any vmashatelstvo in the ship's center of gravity requires constant control. That is why ballast operations are under special supervision. However, ballast water has another side. Although ballast is necessary for operating a vessel, it can pose a serious threat to ecosystems. Do you remember Asian green crabs in European waters, or zebra mussels in North America? The main reason for their spread is precisely ballast water. Together with it, ships perinosit microorganisms, larvae, and pathogens from one region to another. Once in a new environment, these species can destroy local ecosystems, displacing native organisms. To prevent such consequences, sailors are obliged to strictly comply with international and local rules of ballast operations. Ballast water is either treated by special systems or exchanged in the open sea in accordance with established norms. And only after the completion of all inspections, the approval of documents, and the receipt of permits does the vessel get a green light. Now it is the turn of what all this was started for. Work with thousands of vehicles patiently waiting on the decks. And, like everything on this ship, this process is far from simple. Loading vehicles onto quay. Asian beauty is a real art. Each deck is rashitna for certain types of vehicles, taking into account weight and dimensions. There is no randomness here. Everything is subject to a strict plan. But before a vehicle even approaches the ramp, logistics teams begin their work. It is they who Zerania determine where each vehicle will stand, taking into account dozens of factors. One of the key parameters is height. Crossovers and SUVs require more vertical space and are more often placed on the upper decks. Compact sedans and small cars, on the contrary, go to the lower levels, where height is limited. However, height is only part of the equation. The weight of vehicles directly affects the ship's stability. To keep the ship balanced during the voyage, the load is distributed evenly from side to side and from bow to stern. Heavy vehicles, trucks or electric cars with massive batteries, are placed closer to the center of the vessel. This minimizes the risk of heel or longitudinal pitching, especially in storm conditions. The destination is also taken into account. Vehicles that will be unloaded first are placed closer to the ramps. Those that have a longer route ahead go deeper inside the ship. The decks are connected by loading ramps along which vehicles drive up and down. These structures are designed for colossal loads, up to 150 tons. Not only passenger cars can move along them, but also buses or construction machinery. The space between vehicles is minimal. Sometimes literally centimeters remain. Drivers maneuver in tight corridors, demonstrating filigrane precision. A mistake here is unacceptable. After placement, the vehicles must be reliably secured. Although the exact details are not always published, one thing is clear: the ship is constantly subjected to vibrations, rolling, and the impact of bad weather, which means nothing should shift from its place. Wheel chocks are used, made of durable rubber or heavy plastic. They are pressed tightly against the wheels and sometimes additionally fastened to the deck with bolts. Tie-down straps are used, fixing the vehicles from the sides and vertically. They are attached to special points on the body and to metal rings built into the floor. For especially heavy machinery, chains are used, which are tensioned with turnbuckles. The decks themselves are coated with anti-slip compounds, especially important on inclined sections. The decks are equipped with powerful ventilation systems that prevent the accumulation of exhaust gases during loading and unloading. In addition, fire detection and extinguishing systems are installed on every level, from carbon dioxide systems to sprinklers. This is necessary, given the presence of fuel, oils, and electrical components. But even when all safety measures are followed, one question remains. But what happens if something still goes wrong? Even with strict adherence to all procedures, one mistake, an incorrect calculation, uneven loading, or improper ballast work can become fatal. Sometimes the difference between a stable vessel and an overturned hull is measured by only a few tons or one wrong action. And in the history of maritime transport, there has already been a case that became a clear and frightening example of what such a scenario leads to. The ship MV Golden Ray was a large car carrier capable of transporting more than 4,000 vehicles. In September 2019, it was leaving the port of Brunswick in the state of Georgia when the catastrophe occurred. Almost immediately after leaving the harbor, the ship began to lose stability and eventually capsized, ending up on its side in the St. Simons Sound Strait. This incident quickly turned into one of the most expensive and dangerous environmental threats in the history of maritime shipping. The investigation showed that the cause of the accident was a combination of factors: incorrect ballast operations and uneven cargo distribution. The ship proved incapable of compensating for the shift in the center of gravity, and the balance was lost. The danger was not only in the hull itself. On board, there were 24 fuel tanks filled with fuel. In addition, thousands of vehicles contained motor oil, cooling liquids, and other technical compounds. The risk of a large-scale spill was colossal. Any leak could have caused irreparable damage to the coastal ecosystem. Pressure from the public and environmental organizations grew with each day, and time was playing against the rescuers. To eliminate the consequences, a large-scale salvage operation was deployed. The key element was VB-10,000, a giant floating crane with two powerful booms designed for super-heavy lifts. Its task was not to raise the ship as a whole, but to carry out a much more complex operation. The hull of MV Golden Ray was decided to be cut into 8 enormous sections. For this, a special diamond chain was used, a tool capable of cutting through thick layers of metal. And this was not at all the kind of chain you can find in your grandmother's jewelry box. Each fragment weighed thousands of tons. After separation, they were lifted one by one and placed onto barges for subsequent transportation and disposal. However, cutting the hull was associated with an additional threat. Inside the ship were ostatki of fuel, oil, vapors, and gases. High temperature from the cutting equipment could have led to ignition, and a fire under such conditions would have turned a complex operation into a real catastrophe. Therefore, every stage of dismantling was planned with jeweler's precision. Special methods of cooling, monitoring the atmosphere inside the hull, and constant fire safety control were used. The entire operation took more than 2 years. Its cost exceeded $1 billion, which made the cleanup of the consequences of the accident one of the most expensive in the history of maritime transport. But in the end, the work was completed successfully. The ship was fully dismantled, the fuel removed, and the ecosystem received a chance to recover. The Golden Ray catastrophe became a turning point for the entire industry. It clearly showed that proper ballast management is not a formality, but a matter of the ship's survival. A mistake here can literally overturn a vessel. After the accident, measures for multiple verification of cargo securing were strengthened, safety standards were revised, and requirements for firefighting equipment and extinguishing systems became even stricter. Many of these measures today are considered mandatory and are applied on ships all over the world. The story of such giants as Asian Beauty is not just a tale about transporting vehicles. It is a complex system where every detail matters, from ballast tanks to tie-down straps, from documents to the ecosystems overboard. And it is precisely thanks to this endless control, strict rules, and the lessons of past catastrophes that such ships continue to do their work. That is all. See you in the next story. But car carriers are far from the limit of modern marine engineering. There are vessels that take the scale of container transportation to an entirely new level. Imagine a ship larger than a skyscraper, heavier than a city, and more valuable than gold. It does not carry people, it carries the world. Every container on board is food, technology, clothing, and the future of entire nations. Today, you will see how humanity built ocean giants that global trade depends on, and why one of them changed the rules of the game forever. Among all container ships in operation today, one carries the title of the largest container ship ever built by humans. This is Ever a Lot. The container ship Ever a Lot was first launched in June 2022. Its dimensions are astonishing. The overall length of the vessel is 1,339 feet and 1 inch, and the width reaches 200 feet and 2 inches. The cargo capacity of this sea giant is 24,400 TEU, which allowed it to surpass the previous record holder, the ship Ever Ace, which could carry only 23,990 TEU. Ever a Lot sails under the Panamanian flag and is operated by one of the most famous container companies in the world, Evergreen Marine Corporation, based in Taiwan. The design of the vessel was carried out by the shipbuilding group Hudong Zhonghua Shipbuilding Group. One of the key features of the container ship is its enormous deck with an area of 24,000 square meters. That is approximately 3.5 times larger than a standard football field. The ship's cargo hold reaches a height of 108 feet, and the maximum capacity is 24,400 TEU. In a single voyage, Ever a Lot is capable of transporting up to 240,000 tons of cargo. The containers on board can be stacked to a height comparable to a 22-story building. The sight of such a ship in a port or on the open sea makes a truly overwhelming impression. However, it is not only the size that impresses. Ever a Lot was designed with a focus on maximum energy efficiency. Shipbuilders applied the latest hydrodynamic optimization technologies, thanks to which the ship can carry colossal cargo at high speeds while consuming significantly less fuel. This not only reduces operating costs, but also decreases harmful impact on the environment, which is becoming an increasingly important factor in the modern maritime industry. The music rises again, but before such giants enter full operation, they must undergo serious tests. Before official entry into service, every container ship is required to undergo so-called sea trials. During these trials, specialists carefully check the vessel's characteristics, its seaworthiness, and compliance with established safety standards. The purpose of sea trials is to make sure that the ship can operate safely and efficiently in real conditions on the open sea. During the tests, various systems and units of the vessel are checked, including the main engine, navigation equipment, as well as conditions for the crew. One of the key aspects of the trials is checking the strength and stability of the ship. Specialists evaluate how effectively the stabilization system works, and whether the ship can confidently stay afloat in high waves and strong winds. In addition to assessing hull strength, during sea trials, special attention is paid to the container ship's maneuverability. The vessel must confidently execute turns, effectively gain and reduce speed, and accurately respond to control commands. The purpose of these trials is to determine whether the giant ship can move with enough flexibility to safely avoid obstacles, maneuver in narrow straits, and prevent collisions with other vessels in the open ocean. Maneuverability trials are especially important given the colossal size of modern container ships. An error in operating such a vessel can have serious consequences, so every parameter is checked with maximum precision. After completing sea trials, the container ship goes through the next mandatory stage, dry docking. This is a process of detailed inspection of the vessel aimed at identifying possible damage or defects in key structural elements. Dry docking is carried out in port and makes it possible to determine what types of cargo will be transported, as well as what preparatory work needs to be completed before container loading begins. It is at this stage that all technical details affecting the safety and efficiency of the future voyage are clarified. It is important for the crew to understand in advance what cargo stowage plan will be used. This plan determines the exact placement of containers on the vessel and plays a critically important role in organizing transportation because it directly affects stability, safety, and the ship's maximum loading capacity. After all inspections are completed and the stowage plan is approved, the container ship is considered fully ready to go to sea. During the operation of a container ship, it is extremely important to constantly maintain the vessel's balance, especially during the process of loading and unloading containers in ports. One way to achieve this is to stack containers gradually, distributing the load evenly from left to right or vice versa. This approach helps avoid list and preserves the ship's stability at all stages of loading. Large freight trucks and powerful port cranes are used to transport containers. After being lifted by the crane, the container is carefully placed on the deck or in the hold and immediately secured with special locks. This prevents the cargo from shifting and eliminates the risk of containers falling overboard. The process of securing containers on a ship requires highly qualified skills and strict compliance with safety procedures. This stage is called lashing. Lashing includes the use of metal fittings, cables, and locks that reliably hold the containers in place even in heavy rolling and unfavorable weather conditions. Loading and unloading containers are usually carried out under extremely tight deadlines. High-speed operations are necessary to maintain the pace of global trade, while all actions must remain economically efficient and maximally safe. The music builds, but even a perfectly loaded ship is not insured against the dangers that awaited on the open sea. In addition to difficult weather conditions such as storms, high waves, and hurricane winds, container ship crews also face another serious threat: maritime piracy. Pirates stop at nothing. They can attack a vessel, cause significant damage to the carrier company, and endanger the lives of crew members. Most often, attacks occur on busy shipping routes that are regularly used by cargo ships and tankers. One of the most dangerous regions in terms of pirate activity is considered to be the Gulf of Aden, located in the Indian Ocean between Yemen and Somalia. Fortunately, most modern container ships are equipped with reliable defense systems designed to repel pirate attacks. One of the most common means of defense is water cannons. This method has been used for many years and has proven its effectiveness. Water cannons create a powerful stream of water that floods or destabilizes small pirate boats, which are significantly smaller than container ships. The effectiveness of such systems is constantly increasing thanks to the introduction of new technologies and the expansion of equipment functionality. In addition to water cannons, large ships also use long-range acoustic devices that emit sharp, high-frequency sounds. These signals are extremely unpleasant to the ear and force pirates to keep their distance. Additionally, barbed wire barriers are installed on board, which hinder attempts at boarding. A logical question arises: how is everyday work arranged on a container ship? As a rule, watches on the vessel are distributed throughout all 24 hours. Each shift lasts from 4 to 8 hours, depending on the position and duties of the crew member. Crew functions differ greatly. Some are responsible for navigating the ship, others for cargo control and stowage, and others handle repairs and technical maintenance of equipment. There are also specialists who monitor weather conditions and make decisions in case of emergencies. Container ships can remain at sea for many days and even weeks without entering port. That is why all necessary conditions for polnocenny life of the crew are provided on board. As a rule, container ships are equipped with living cabins, each of which is furnished with basic furniture, a bed, a table, chairs, a wardrobe for personal belongings, and a private bathroom. These spaces become a temporary home for sailors far from land. In addition to living quarters, there is a mess hall and a galley on board. The galley is equipped with standard kitchen equipment comparable to a full professional kitchen. Food is prepared here every day for the entire crew, because regular and quality pitanya directly affects performance and the safety of the vessel. Balanced nutrition helps maintain the crew's strength, allowing the ship to continuously perform its tasks and follow the established route without delays. However, nutrition is only part of sailors' everyday life. Work at sea requires strong health, so container ships usually have small gyms on board. Here, crew members can train, maintain physical fitness, and relieve tension after long shifts. Long isolation from family and a familiar social environment often leads to feelings of loneliness and psychological fatigue. To cope with this, the crew is provided with various forms of leisure. Sailors can watch films and television programs, read books, play video games, or play billiards. These simple razvlečenia help maintain emotional balance during long voyages. Despite the distance from shore, modern container ships are equipped with internet connectivity, allowing the crew to stay in touch with loved ones and follow news from around the world. The internet is also used to receive operational information and updates necessary for safe navigation. Looking at the processes of loading and unloading containers, as well as the daily life of the crew, it becomes obvious. Without these ships, modern global trade simply could not exist. Export and import of goods on a global scale would be impossible without huge container ships that connect continents every day, ensuring stable and efficient movement of goods around the world. It is here that a new chapter begins, the fight for the title of the largest container ship on the planet. As of today, the title of the largest container ship in the world belongs to MSC Arena class. The vessel MSC Arena was built and put into operation in 2023 and sails under the Liberian flag. Its construction was carried out at the shipyards of the Chinese shipbuilding group Yangzijiang. The length of the vessel is 1,312 feet, and the width is about 211 feet. The gross tonnage reaches 233,000 tons. Although in length and width, MSC Arena is comparable to other modern container ships, it is the cargo capacity that makes it unique. This vessel can carry more containers than any other operating container ship in the world. MSC Arena surpassed the previous record holder, a vessel of the OOCL Spain class, by more than 150 TEU. Special attention during the design of MSC Arena was given to environmental issues. The vessel is designed so as to emit 3 to 4% less carbon emissions than similar ships of previous generations. During its first voyage, MSC Arena traveled the route from Qingdao to Busan, then returned to China, after which it headed to Singapore, Italy, and Spain through the Suez Canal. On the return journey, the vessel called at ports in Saudi Arabia and the United Arab Emirates. The music changes, but MSC Arena is far from the only giant of the oceans. Container ships of the OOCLG class were built by the South Korean company Samsung Heavy Industries. The cost of building each vessel reached $950 million. These ships are intended for operation by the Hong Kong shipping company Orient Overseas Container Line. A container ship of the OOCLG class has an overall length of 1,312 feet, a width of 211 feet, and a gross tonnage of 235,041 tons. The maximum cargo capacity reaches 24,188 TEU. The vessel design complies with current energy efficiency index requirements making it not only powerful, but also comparatively ekologiczny. Each vessel of the OOCLG class has impressive engineering parameters. The width of the hull on the molded line is 192 feet, the depth reaches 106 feet, and the draft is 52 feet. The container ship is equipped with a powerful engine developing up to 14,940 horsepower at 79 revolutions per minute. This engine was specially designed with an emphasis on reducing fuel consumption and lowering carbon dioxide emissions compared to ships of previous generations. To perform mooring operations and anchor maneuvers, the ship is equipped with specialized crane systems produced by a Polish company. These mechanisms allow operations to be carried out safely and accurately, even in difficult port conditions. The 1I class, also known as the OI class, is one of the most modern classes of container ships in the world. These ships were developed and built for the company Ocean Network Express, widely known by the abbreviation 1. Ships of the 1I class became the last of 6 vessels introduced into service on this route, starting in June 2023. The length of the container ships of this class is 1,312 feet, the width is 211 feet, and the maximum capacity reaches 24,136 TEU. One of the key design features is a unique arrangement that allows containers to be loaded significantly closer to the bow of the vessel, up to the mooring deck. This solution increases overall loading efficiency and optimizes weight distribution. Container ships of the 1I class became the first vessels in whose construction a technology to prevent the propagation of brittle cracks was applied. Ultra-thick, high-strength steel plates are also used, which significantly increases the reliability of the hull under extreme loads. A MAN B&W engine with a power of about 62 million kilowatts is used as the main power plant, providing the vessel with a cruising speed of 22 knots, which corresponds to approximately 25 miles per hour. Container ships of the MSC Tessa class, also known as the Hudong class, were built by the Chinese State Shipbuilding Corporation CSSC and are operated by MSC. This class of vessels was created based on the Ever A class design and began active operation in 2023. The main direction of work for these ships is cargo transportation between Europe and East Asia. MSC Tessa has an overall length of 1,312 feet, a width of 202 feet, and a gross tonnage of about 237,057 tons. The maximum cargo capacity reaches 24,116 TEU. The container ship is equipped with a 2-stroke MAN B&W engine, developing power up to 92,000 horsepower. This allows the vessel to reach a maximum speed of 24 knots, which is equivalent to approximately 27 miles per hour. Special attention during the design was given to efficiency. The vessel is equipped with a revolutionary bubble lubrication system, in which air bubbles are supplied along the hull. This reduces water resistance and makes it possible to reduce emissions by approximately 4%. To increase the level of safety, MSC Tessa is equipped with a modern global maritime safety system that allows operational responding to any emergencies on board. Evergreen. A class container ships of 2022 are part of the Ever A class series and are still actively operated. In total, 5 vessels of this class remain in service. The ships were built by the CSSC Corporation and began service in 2022. 2 vessels are part of the Green Compass Marine Fleet, and 3 are operated directly by Evergreen, which also owns 2 more ships ordered from CSSC. A class of 2022 has a length of 1,312 feet, a width of 202 feet, and a gross tonnage of 235,000 tons. The maximum capacity reaches 24,400 TEU. In addition to the 2022 version, the Evergreen A-Class series also includes an earlier design introduced into service in 2021. This variant consists of 13 actively operating container ships. Evergreen A-Class of 2021 is operated by the Taiwanese company Evergreen Marine Corporation. Unlike the newer modification, these ships have a maximum capacity of 23,990 TEU. 6 vessels of this series were built by Samsung Heavy Industries in South Korea. Their maximum length is 1,312 feet. The width is 202 feet. The draft reaches 55 feet, and the gross tonnage is about 235,000 tons. The HMM Algeciras class is a series of 12 container ships built for the company Hyundai Merchant Marine, also known as HMM. These container ships, with a maximum capacity of 23,964 TEU, were built by Daewoo Shipbuilding, which today is known as Hanwha Ocean. After construction was completed, the vessels were delivered to the customer and began operation in 2020. The length of the ships of this class is 1,312 feet. The width is slightly smaller, about 200 feet, and the gross tonnage reaches 228,000 tons. Thanks to their size, the ships of the HMM Algeciras class were able to surpass the previous record holder, the MSC Gulson class, whose capacity was 23,756 TEU. There is also an alternative version of the HMM Algeciras ships, assembled by Samsung Heavy Industries. Formally, these vessels belong to the same class, but there are a number of differences between them. If the previous ships were built by Daewoo, then these container ships were assembled at Samsung shipyards. A total of 5 vessels were built, the flagship of which was HMM Oslo. Sometimes this subgroup is called the Oslo class. The dimensions of the ships remain the same, a length of 1,312 feet, a width of 202 feet. However, the gross tonnage increased to 232,000 tons, and the maximum cargo capacity amounted to 23,820 TEU. The MSC Gulson class is a series of container ships built by 2 South Korean companies, Daewoo Shipbuilding and Samsung Heavy Industries. These vessels were ordered by Mediterranean Shipping Company, or MSC, and have a maximum capacity of 23,753 TEU. At the moment of their launch in 2019, MSC Gulson class container ships were considered the largest in the world, surpassing the previous leader, the OOCL Hong Kong class, whose capacity was 24,013 TEU. The versions of the vessels built by Daewoo and Samsung have the same length, 1,312 feet, and the draft is 54 feet and 2 inches. However, the width differs. Daewoo vessels have a width of 200 feet and 2 inches, while the Samsung version is 201 feet and 9 inches. Notably, MSC Gulson became the first container ship in the world capable of razmashat 24 containers in width on the deck. The list of the largest container ships is concluded by the Berlin Express class, owned by the German operator Hapag-Lloyd. These vessels actively operate on routes between the Far East and Northern Europe and were first delivered to the customer in 2023. Berlin Express container ships have a length of 1,312 feet, a width of 200 feet, and a gross tonnage of about 236,764 tons. The maximum cargo capacity reaches 23,664 TEU. The ships are equipped with a dual-fuel power plant and can already use liquefied natural gas today. In addition, the design allows the use of alternative fuels, including ethane. The vessels sail under the German flag and are equipped with MAN main engines with a power of more than 75,000 kilowatts, which provides a cruising speed of about 22 knots, or approximately 25 miles per hour. The music gradually fades. These container ships are not just ships. They are the backbone of global trade and the hidden mechanism thanks to which the modern world works without stopping. While we live our everyday lives, these giants cross oceans, connecting continents, countries, and economies. Their size is astonishing. Technologies become more complex, and routes become longer. And while such ships go to sea, global trade continues to move forward. The next time you see a container ship on the horizon, remember, before you is not just a ship, Before you is the force that keeps the world in motion. The music fades. And yet, even the largest commercial ships are only one part of global logistics. When it comes to military equipment and entire armies, the scale of operations becomes even more impressive. Before us is a USNS, a gigantic transport ship capable of carrying so much U.S. Marine Corps equipment that it would be enough to wage a full-scale war. But delivering that power to the other side of the planet is a process far more complex than simply driving the vehicles onto the deck and heading out to sea. Behind the scenes of this operation are thousands of precisely calibrated steps. Here, an error measured literally in inches can lead to catastrophe. The ship will lose stability, or equipment worth billions of dollars will be damaged or destroyed. And this entire chain of decisions begins right here, at Naval Base San Diego. Early in the morning, Marines from Combat Logistics Regiment 1, together with sailors from Navy Cargo Handling Battalion 1, begin loading. Their task is to move a full set of equipment for one Marine brigade intended for deployment to the Middle East. A long line forms on the pier. The first of 742 vehicles slowly approaches the ship's ramp and stops, not because something went wrong, but because this exact vehicle must be the first to board. We are talking about the M1A1 Abrams tank. Its priority is dictated not by symbolism and not by convenience, but by strict requirements of the load plan. A load plan is not just a layout for arranging equipment. It is a detailed technical document that defines the exact position of every single piece of cargo inside the ship, with accuracy down to 1 inch. The reason is the ship's center of gravity. On an empty USNS-type ship, the center of gravity is located at roughly 30 feet above the keel. While the vessel is empty, there are no problems. It sits level, reacts calmly to waves, and maneuvers confidently. But everything changes when about 8,000 tons of equipment and gear begin to be loaded aboard. If you overload the port side, the ship will begin to list. If you shift the weight forward, the bow will drop and the ship will start cutting into waves. If you overload the stern, the propellers can partially come out of the water in heavy seas. That is exactly why every vehicle is positioned so that the center of gravity remains within 6 inches of the optimal value, on a ship nearly 950 feet long. The Abrams climbs the ramp at exactly 3 miles per hour. It is not simply driving into the vessel, but strictly to position Charlie 7 on the third deck. The hull is oriented toward the starboard side, and the turret is rotated to 270 degrees. This is critical, because the tank's turret alone weighs 22 tons. Turn it forward, and you shift that weight toward the bow, rotate it aft, toward the stern, multiply that by dozens of tanks, and the ship's trim can easily move by several degrees. Inside the tank, the driver can barely see anything. The ramp has an incline of about 12 degrees, and all that is in front of his eyes is a steel deck and shadows. So movement is possible only thanks to ground guides. Marines give hand signals, a simple sign language that has not changed since the Second World War. Engine revolutions are kept at around 800 per minute. Higher, and the tracks can slip on the anti-skid surface. Lower, and there may not be enough power to climb. Stopping halfway up the ramp is dangerous. Getting 68 tons moving again on a steel-inclined surface is almost impossible. While the Abrams slowly climbs the ramp, a process is happening inside the ship that neither the driver nor observers on the pier can see. The automatic ballast system comes online. When 68 tons of mass begin moving from sea level up to the third deck, the ship's center of gravity shifts upward and toward the stern. Onboard computers register this instantly. In response, seawater begins pumping between ballast tanks. Right now, about 10,000 gallons of water are moving from forward compartments to aft ones to compensate for the shift in mass. The vessel must remain almost perfectly level. The allowable list is no more than half a degree. Any excess changes the ramp angle so much that the next vehicle can simply get stuck while driving on. The tank reaches its position and stops exactly at the calculated point. Immediately after stopping, Marines dive under the tank's hull. They work with chains, each rated for a load of 15,000 pounds. One Abrams requires 22 such chains. The reason lies in the physics of the ocean. In the open sea, the ship can encounter waves up to 30 feet high. When the ship drops into a trough between waves, negative acceleration occurs, and the tank literally tries to lift off the deck. When the ship climbs a crest, the load reaches 2G. In that moment, the tank's mass doubles. It weighs not 68, but 136 tons. The chains must hold it in both scenarios. The key factor is the installation angle of the chains. Each must be secured at an angle from 30 to 60 degrees. At 45 degrees, the chain delivers maximum holding force. At 30 degrees, it provides about 7,500 pounds of vertical force, but reduce the angle to 20 degrees, and holding capacity drops to 5,000 pounds. At 10 degrees, down to only 2,600. An error in angle means that in the first serious storm, the tank will tear free from its restraints and turn into a 68-ton destructive projectile inside the ship's hull. Lever-type tensioners are used to tighten the chains. These are mechanical devices providing a 30-fold mechanical advantage. A person applies about 50 pounds of effort, and the chain develops tension of about 1,500. Tightening is brought to the stop, after which the mechanism is loosened by a quarter turn. This is done intentionally. Metal expands and contracts with changes in temperature. A chain tightened in the morning in San Diego at 70 degrees can expand so much by midday heat at 95 that it can simply snap from excessive tension. Behind the Abrams, the next machine is waiting on the pier, a rough terrain container handler. This is not a warehouse forklift, but a diesel crane on wheels with a telescopic boom, capable of stacking containers 3 high. The operator sits in a cab that tilts back nearly 90 degrees. This allows him to see how the spreader connects to the container's corner castings. Those castings must align with accuracy to within half an inch. The slightest deviation, and the twist locks will not engage. In that case, lifting a 40,000 load will be held solely by friction. The handler picks up a quadcon, a quarter of a standard container, loaded with spare parts. Its mass is about 8,000 pounds. At the moment it leaves the ground, the entire machine tilts slightly forward. The operator watches the stability indicator, a gauge showing how close the machine is to tipping over. With the boom fully extended, the handler can lift no more than 30,000 pounds. In the retracted position, up to 60,000. A mistake in calculations, an incorrect boom reach, and the machine can overturn, flinging the container forward like a catapult. Nearby, 7-ton military trucks undergo preparation for loading. Marines work by a checklist that seems excessive until you understand the cost of error. The fuel level must be strictly at 1/4 of a tank. An empty tank is dangerous because of vapor formation. A full one is dangerous because of thermal expansion and extra weight. One fully filled tank adds hundreds of pounds of mass. If you multiply that difference by hundreds of vehicles, the load plan is disrupted by dozens of tons. After checking fuel, Marines move to the next mandatory stage, disconnecting the batteries, not simply turning them off, but physically disconnecting them. The terminals are removed, insulated, and additionally wrapped with tape. Even when disconnected, a battery loses about 2% of its charge per week due to internal chemical processes. But if left connected, the situation becomes worse. Modern equipment constantly consumes energy. Onboard computers, clocks, monitoring systems. In a few weeks, the battery is completely discharged. After 3 months at sea, it is no longer just dead. Sulfation occurs. Crystals form on the lead plates that permanently deprive the battery of its ability to hold a charge. A battery costing several $100s turns into useless cargo. Sensitive equipment is removed completely. Radio systems worth tens of thousands of dollars are dismantled, packed in vapor barrier bags with desiccants, and placed into climate-controlled containers. Salty sea air is a deadly enemy of electronics. It penetrates the smallest gaps, settles on contacts, and in a matter of weeks, turns circuit boards into a green mass of corrosion. One drop of condensation inside a thermal sight, and fungus begins developing on the lens. The result is an expensive replacement and a shooter deprived of sight in combat. Some vehicles require a separate approach. A Humvee with an anti-tank missile system climbs the ramp. The launcher adds about 6 feet of height and several thousand pounds of mass, and all of that weight is positioned high. The center of gravity shifts sharply. While climbing the ramp, ground guides watch for the slightest list. Any extra angle, and the vehicle can tip over. That is why such equipment is placed on the second deck, where overhead clearance allows for the dimensions and the subsequent tightening of chains that will pull the vehicle downward. A separate problem is created by light armored amphibious vehicles with 8 wheels. They weigh about 14 tons, but were originally designed to float, and that means their center of gravity is intentionally placed higher than normal. On the ramp, such vehicles behave unstably. The driver can barely see through narrow viewing blocks. The ground guide is forced to stand at a strictly defined point so that his gestures are visible in a window the size of a pocketbook. Any coordination mistake here can lead to a rollover. The most massive vehicles cannot be driven aboard under their own power. The ship's own cranes are used for them. The USNS is equipped with 2 deck cranes with lifting capacity of 55 tons each. In tandem, they can lift up to 110 tons. When it is time for an armored recovery vehicle with a mass of about 70 tons, both cranes work simultaneously. The operators cannot see each other, so all actions are directed by a single cargo master over radio. He distributes the load, gives lift commands, and synchronizes movement. Any mistake in transmitting a command, and one crane can take the full weight. In that case, there is a risk of cables snapping, rated at the limit of their loads. The loading process lasts almost 2 weeks. Day after day, each vehicle goes through the same procedure: preparation, positioning, securing. The ship gradually turns into a dense, perfectly calculated volume of metal, fuel, and equipment. By the 3rd day, containers with ammunition begin arriving. Their placement follows separate rules. Ammunition cannot be near fuel. White phosphorus requires special ventilation zones. High explosives are placed deeper inside the hull, where bulkheads are thickest. If something goes wrong, there must be as much steel as possible between the explosion and the ocean. When the last vehicle is secured deep inside the ship, the USNS leaves San Diego Bay. From this moment, 742 pieces of equipment begin a 90-day journey not simply across the ocean, but through gradual degradation. The first enemy is temperature cycles. In tropical latitudes, cargo decks heat up to 130 degrees by day, and at night the temperature drops to 50. A difference of 80 degrees repeats every day. Metal expands and contracts, rubber seals lose shape, chain tension constantly changes. A chain tightened in San Diego with a force of 5,000 pounds, after thermal contraction, can hold significantly more, and after expansion, on the contrary, weaken. The balance calculated on the pier gradually drifts. Ships are not airtight. They are not submarines. Salty sea air gets inside through ventilation systems, hatches, and door seals. It settles as crystals on all exposed metal surfaces. Aluminum becomes covered with white corrosion powder. Steel rusts. Brake discs grow a reddish film that over time literally fuses with the brake pads. After 3 months, such brakes are effectively locked. Another problem is condensation. Warm, humid air meets cold steel bulkheads, and a real rain begins inside cargo holds. Water accumulates on hoods, runs down windshields, and through breathers gets into fuel tanks. Diesel fuel and water do not mix. Water settles at the bottom, where it begins destroying fuel pumps. The fuel itself stratifies during the crossing. Heavy fractions sink, light fractions rise. Additives that prevent microorganism growth settle, and lubricating additives float. What was poured in as quality fuel turns after months into a layered mixture of questionable quality. Even disconnected batteries keep degrading. A battery capable of delivering 800 amps of cranking current in San Diego after 3 months at sea sometimes produces only 200. Some batteries swell from heat, others crack from constant hull vibration. Worst of all are those that begin to leak. Acid corrodes battery boxes and mounting elements, creating problems that are discovered only during unloading. After weeks and months of travel, the ship enters a port in Saudi Arabia. And here it becomes clear. Unloading is not a mirror image of loading. If during loading the equipment boarded strictly according to the balance plan, now the order is determined by combat priorities. Vehicles must leave the ship not in the order they were loaded, but in the order they will be needed in the first hours of the operation. The ship uses 3 ramps with different capabilities. The stern ramp is rated for loads up to 112 tons. The 2 side ramps, up to 40 tons each. The stern ramp can change its incline angle from 0 to 18 degrees, depending on water level and pier height. The ballast system continues working during unloading as well. As equipment leaves the upper decks, water is pumped into aft compartments, keeping the ramp angle within 1 degree. Any deviation complicates the descent of vehicles and increases the risk of damage. Before vehicles can leave the ship, the chains must be removed. After 90 days at sea, this proves significantly more difficult than during loading. Thermal cycles and corrosion have changed the tension. Chains tightened with a force of 5,000 pounds can now hold significantly more. They are removed in a strict sequence, starting with the upper ones so that the vehicle does not tip forward when the lower ones are loosened. Each tensioner requires about 15 turns in the opposite direction, and the effort required for the work increases threefold. After removing the chains, equipment begins moving between decks via the ship's internal ramps. These transitions have fixed angles, about 15 degrees between the second and third decks, and about 12 between the first and second. The width of the ramps is about 20 feet, but with safety zones the working space narrows. Strict rules apply here. Speed must not drop below 5 miles per hour. Stopping halfway up is dangerous. Because of the mass of the equipment and the incline, restarting may be impossible. Any delay blocks the movement of other vehicles and slows the entire operation. In parallel with unloading, the crew deploys an offshore fuel transfer system. It is used in cases where shore infrastructure is absent or unavailable. Flexible 6-inch hoses are connected to the ship, capable of pumping up to 600 gallons of fuel per minute. The system maintains pressure of about 50 pounds per square inch and is equipped with water separators that remove contaminants accumulated during the sea passage. Fuel can be delivered either to floating storage tanks or directly to shore facilities. If using a commercial port is impossible, the Navy uses the Navy lighterage pontoon system. A bridge about 2,100 feet long is assembled from self-propelled sections from the ship to the shore. Each section has fixed dimensions, shallow draft, and connects to the next with automatic locks. Such a bridge can withstand waves up to 4 feet high and pass equipment weighing up to 75 tons. Docking requires high precision. Allowable misalignment between sections does not exceed a few inches. Hydraulic systems pull the elements together while the ship holds position using dynamic positioning. When the pontoon system is unavailable, special flat deck tugs are used. They receive equipment directly from the ship's side ramp. Each such tug can carry up to 180 tons and deliver the cargo to shore in a matter of minutes. Loading requires precisely matching the tug deck height and the ship's ramp. This is achieved by ballasting, which allows the tug's draft to be changed by several feet. A miscalculation in height creates a risk of damaging equipment during descent. In a combat situation, the ship can switch to emergency unloading mode. All 3 ramps are lowered simultaneously. Equipment leaves the ship at the maximum safe speed, up to 10 miles per hour on the ramps and up to 15 on level decks. The internal traffic control system uses light signals, Green, move, red, stop, yellow, caution when transitioning between levels. In this mode, one deck can be cleared in about 20 minutes instead of 1.5 hours under the standard procedure. An automated accounting system records every vehicle at the moment it crosses the ramp edge. Laser sensors measure dimensions and mass distribution. This data is immediately transmitted to shore services for forming convoys. If the system detects a lateral imbalance of more than 500 pounds, the equipment is automatically sent for an additional suspension check even before it leaves the port area. But unloading is only the beginning. At the rear staging area beyond the port, all 742 vehicles face the next stage, restoring combat readiness. Marines have only 4 hours to turn equipment that survived 90 days of maritime degradation into units ready for battle. Battery replacement runs on a conveyor principle. Under ideal conditions, a Humvee battery is replaced in 3 minutes. If the mounts are rusted, more time is added. Some battery boxes are so damaged by acid that they crumble at the first touch. Such vehicles require urgent repair. Fuel systems are checked on nearly half the equipment. Water is removed manually by purging the system until clean fuel appears. Turbochargers that sat idle for months sometimes fail at the first rise in RPM. Brakes are checked in a simple way, by tapping. A ringing sound means serviceable. A dull one means heat damage. Optics stored separately undergo defogging and nitrogen purging. A mist-fogged sight means a fighter deprived of sight in battle. As readiness is restored, equipment is distributed among units. If one platoon lacks serviceable vehicles, they are temporarily reassigned from another. The main goal is for the unit to depart en route at full strength and on time. 4 hours after the first vehicle descends, the first convoy leaves the port. The equipment does not sound perfect, but it moves. That is enough to begin the operation. A few hours later, the ship completely clears its decks. An entire brigade of equipment comes ashore. The USNS raises its ramps, turns, and sets course back, leaving behind 742 vehicles that enter a war they began preparing for 3 months earlier, on the other side of the planet. But sometimes, what needs to be moved is not an army, but the protection of a single person. And that is when one of the most complex security systems on the planet comes into play. This is the presidential motorcade at the moment when it moves around the world in such a way that absolutely no one notices it at all. Right now, while President Donald Trump sleeps in the White House, his armored limousine is already on the other side of the planet. It arrived at a warehouse in Qatar, about 6,900 meters from here, and it will wait for its passenger for 3 more days. And this is not a copy, not a backup option. This is that very same car, a 20-ton monster that on Friday will be responsible for the president's safety, has been standing there since Tuesday morning. And if even one officer of a foreign intelligence service figures out how exactly they pulled off this trick, decades of American security development can simply be thrown in the trash. Transporting the presidential motorcade overseas is not shipping your Honda to Hawaii, because the beast is not a car. It is a moving fortress. 8 inches of classified armor, 5-inch bulletproof glass. Doors that, by weight, are comparable to the doors of a passenger Boeing 757. This machine can withstand a direct hit from an RPG, seal airtight during a chemical attack, and simultaneously maintain encrypted communications with the Pentagon while moving at 60 miles an hour. Any intelligence service in the world would pay millions just for the chance to measure that armor with an ordinary ruler. So how does the Secret Service deliver 68 tons of the most sensitive American vehicles to Qatar in a way that no one can study them? The answer begins on Sunday evening at Andrews Air Force Base. At Andrews Air Force Base, loadmasters prepare the Beast for loading into a military transport aircraft, a C-17. This is about as simple as trying to park a bank vault inside an airplane and still make sure the airplane can take off. The limousine's weight is about 20,000 pounds. That is like stacking 6 Toyota Camry cars on top of each other. Every centimeter of its position inside the cargo bay matters. A placement error can shift the aircraft's center of gravity so much that a routine flight turns into the worst nightmare at 30,000 feet. 3 loadmasters spend 45 minutes just to set the car perfectly precisely. Laser guidance systems are used, down to fractions of an inch. Then the limousine is secured with chains that can hold it even in the event of a barrel roll. Nobody wants to test that in practice, but everyone is required to be ready. That same day, the C-17 takes off, using a call sign that will change 3 times before landing. It is like using fake names at a hotel, except the hotel is the entire sky, and the names are hidden from military radars. The pilots have clearance levels that are usually given to people transporting nuclear weapons. The Pentagon's logic is simple. If they trust you with atomic bombs, then you can handle the president's car. In the flight plan, the cargo is listed as diplomatic materials. Formally, that is true, about the same way it would be true to call a shark seafood. Over the next 14 hours, this flying warehouse of armor moves through military air corridors completely separated from civilian aviation. The aircraft is invisible to ordinary radars, is not listed in any public database, and effectively flies across the night sky like Santa Claus. Only instead of gifts, it is carrying state secrets. Inside the cargo bay, there is not only the Beast, there is an entire motorcade, ambulances with blood supplies for transfusion, strictly the same blood type as the president's. Communications vehicles capable of jamming any electronics within a radius of 500 meters. Support vehicles with medical equipment sufficient to turn a Walmart parking lot into a full-scale trauma center. The pilots constantly track the weather at the destination. They are looking for ideal conditions for an unnoticed landing. Better to circle in the air for an extra hour, burning thousands of dollars of fuel, than to land at the moment when a Russian satellite might be watching the area. But before they can even think about landing, the crew must conduct 2 aerial refuelings. The first, somewhere near the Azores. The second, in the eastern part of the Mediterranean Sea. The reason is simple. The aircraft cannot land on foreign territory, even on American bases, without the risk of repeated inspection for listening devices. After the second refueling, upon entering Middle Eastern airspace, the final call sign change happens. And if someone was still tracking this flight, that is exactly how 68 tons of presidential armor disappear in the air, or, to be more precise, materialize in a hangar that is about to become the most American piece of Qatar you have never heard of. The C-17 touches down on the runway of Al Udeid Air Base at exactly 3:17 in the morning local time. This is not a random number. This is the moment when the only people who can observe the landing are Secret Service agents who have been standing on this stretch of concrete since yesterday. No vehicles with orange wands, no standard airfield bustle, not a single ordinary airport employee, only hand signals and encrypted radio messages guiding the massive military aircraft into a section of the base that does not exist on any map accessible through Google. The cargo ramp opens and the night desert air pours inside. Even at 3 in the morning, the temperature here is about 35 degrees Celsius. Qatar does not believe in comfortable conditions, even for top-secret operations. The vehicles begin to roll down the ramp. First, the support transport, then the communications trucks, and only then him, or rather, them. Because there is not one beast, there are 3, absolutely identical. The Secret Service does not acknowledge the concept of a single point of failure when it comes to protecting the president. Each limousine is the same in weight, armor, electronics, and appearance. The column moves slowly across the base, passing Qatari military posts. Their guards suddenly find themselves extremely busy with something in the opposite direction. The vehicles head toward warehouse number 7. 2 days ago, it was an ordinary warehouse building. Now, it is something entirely different. Thanks to diplomatic agreements so complex that State Department lawyers who work with nuclear treaties were needed to formalize them, this concrete hangar is now considered the equivalent of White House territory. Formally, it is still Qatar. Legally, almost Washington. Inside, the warehouse looks more like a hybrid of a high-security garage and a paranoid fortress. The temperature is maintained strictly at 58 degrees Fahrenheit, not for comfort. With an improper temperature regime, the limousine's rubber seals can begin to break down, and damaged seals mean a risk of losing airtight integrity during a chemical attack. Dehumidifiers run without stopping. Excess moisture can disrupt the operation of electronic countermeasure systems. Even the lighting here is designed in a special way. It eliminates any shadows in which a listening device the size of a shirt button could hide. The vehicles are parked in formations that change every 12 hours. Even the parking positions are classified. The 3 identical limousines are positioned to confuse anyone who tries to determine which one will actually carry the president. If someone could take a photo from above, through the roof, they would see 3 absolutely identical cars, and not a single answer. Support equipment creates visual barriers. It is like a shell game. Only the shells weigh about 20,000 pounds each and cost about $1.5 million. Marines arrived here a day earlier on another flight. Officially, they are listed as embassy support personnel. The wording is precise if you consider these limousines a mobile, armored embassy. They establish a security perimeter with a radius of about 2 miles around the warehouse. Equipment is used that can detect drones, ultra-long lenses, even parabolic microphones that look like satellite dishes. For the next 72 hours, they live right inside this hangar. They sleep on cots next to machinery that costs more than they will earn in their entire military careers. They eat MREs, and they guard what is essentially the most expensive garage in the world. In parallel, Secret Service agents conduct checks every 4 hours. Like overly caring parents, they inspect each vehicle for signs of interference. They scan the airwaves for new radio frequencies. They check the undercarriage with mirrors, looking for magnetic devices. They test communication systems, ensuring no one has tampered with them. Outside, everyone plays a complex game of pretending. Qatari military understand that something extremely important is inside, but officially, they know nothing. The base commander provides security and asks no questions. Local intelligence services, which usually record every American movement, suddenly turn into people who see nothing. But the Secret Service works from a different principle. Someone is always watching. The 3 beasts standing in the Qatari hangar really are identical. Not roughly the same, not similar, absolutely identical. The same armor, the same weight, the same electronics, the same every detail. The Secret Service weighs each limousine so that the difference between them does not exceed 5 pounds. And this is not a whim. Americans once learned that foreign intelligence services use ultra-high-resolution imagery to analyze tire deformation. Someone noticed, a heavier vehicle flattens the tires just a little more. A microscopic difference, invisible to the eye, but distinguishable by algorithms. From that moment, the Secret Service began thinking about things like rubber bulge. And yes, this is the level of paranoia required to protect the president. On Friday, when President Donald Trump arrives, all 3 limousines leave the warehouse at the same time. Each by its own route, each under guard. Secret Service drivers, who spent weeks training on an exact replica of the local roads in Maryland, begin what from the outside looks like an automotive ballet. On the runway, while Air Force One slowly taxis, 3 identical beasts constantly switch places. They converge, separate, and rearrange again. And here is the key moment. When the president walks down the stairs, even the drivers do not know which limousine he will get into. The decision comes at the last second, through an encrypted channel from agents aboard the aircraft. They analyze everything: the placement of people, surveillance data, intelligence messages, movement of equipment, and only then do they make the choice. The president gets into one of the beasts, and deliberate motion is created around the other 2. For any observer, it becomes impossible to understand which vehicle actually matters. And those 2 empty limousines are not empty. Inside are Secret Service agents. They sit there, projecting importance. Although, strictly speaking, they really are important, just not in the way the people watching think. During movement, this performance only becomes more complicated. The three limousines swap positions every 30 to 90 seconds. Routes and lane changes are built according to schemes developed by NSA cryptographers. Yes, the very same people who create unbreakable ciphers. Now they are engaged in making vehicle movements mathematically unpredictable. The lead car suddenly drops back. The middle car sharply moves to the side. Even if all of this is filmed from a helicopter, it is impossible to track where exactly the president is. But that is not all. Each beast transmits the same electronic signature, the same encrypted traffic, the same electromagnetic emissions, the same thermal pattern. The Secret Service learned that advanced militaries use signals intelligence to identify the presidential vehicle, about the same way you can find a person by their Wi-Fi signal. Now all three limousines generate false identical noise, turning remote identification into an impossible task. The communications vehicles amplify the effect. They not only jam signals to prevent remote detonation of explosives, but also create fake cell towers. Any attempt to coordinate an attack by phone suddenly routes through NSA servers, which, mildly speaking, rarely fits into a malicious actor's plans. This electronic bubble extends 500 meters in all directions. Inside it, drones lose GPS and fall. Smartphones stop working. Even modern cars with wireless keys refuse to start. It is a zone where technology stops obeying its owners. Behind this visible illusion, another level of protection is hidden. There is a fourth beast. It does not participate in the showy performance. It does not appear on cameras. It waits in a protected position between route points. If something breaks, gets delayed, or raises suspicion, it is the one that becomes the backup option. Support vehicles carry spare wheels that weigh exactly as much as the beast tires. An ordinary tire would change the vehicle's behavior on the road, and any change is a potential risk. The motorcade even carries spare doors. The Secret Service once learned that a damaged door can jam, locking the president inside. And headlines like, "The president could not leave the vehicle," are a scenario that suits no one. This game extends not only to vehicles, but also to roads. For each destination, the Secret Service plans 3 routes. Which one will be used is decided after the movement has already begun. Local police block all 3. Helicopter observers cover all 3. The real path is chosen based on real-time data, intelligence information, weather conditions, traffic conditions, and sometimes simply the intuition of agents who have been doing this for decades. From the outside, it seems that the motorcade confidently moves through the streets. In reality, it is a constantly changing decision tree executed at a speed of about 40 miles an hour. When the visit ends, the work only begins. The moment Air Force One lifts off with the president on board, an evacuation operation is launched. And it is exactly here that the Secret Service becomes truly paranoid. They have 18 hours to check every vehicle and disappear before foreign intelligence understands. The motorcade is temporarily vulnerable. While the president's aircraft climbs to cruising altitude, technical teams surround the vehicles with equipment so sensitive that it can detect a baby monitor from several blocks away. They look for listening devices. They check for traces of explosives. They conduct a digital check of all systems. Unofficially, they call it an electronic colonoscopy. They care about everything: modified firmware, hidden access channels, any signs of remote interference. Even GPS systems are replaced completely. Previously, the Secret Service learned that attackers can embed microscopic time distortions that allow the vehicle to be tracked later. Invisible breadcrumbs. Then the strangest stage begins. Each vehicle is treated with chemicals that destroy DNA and fingerprints. Not because of local forensic experts. Foreign intelligence services collected biological traces, creating databases for profiling Secret Service agents. The evacuation happens completely differently from the arrival. Different crews, different routes, different time. If the arrival was at night, the departure will be in daylight. The Secret Service follows a simple rule. If someone watched the arrival, they will wait for a repeated pattern. The C-17 returns to Andrews Air Force Base, while another aircraft is already carrying the vehicles to the next point on the president's itinerary. These operations run in parallel. Motorcades are constantly in motion. This is the most expensive juggling act in the world, where every mistake costs far too much. When everything ends, it seems like nothing ever happened. No traces, no witnesses, just a president who appears in another country, and a car that seems to have emerged from nowhere, and then disappears again. That is what security looks like at the level where paranoia is not a weakness, but a necessity.